Welcome everyone. So in the last class we have started our discussion on MMC and its working principle, and we have seen that MMC will be having modular in configuration. It addresses all the limitation of multi-level converter, that is multi-level converter required quadratic increment in the device count when we were trying to increase the number of levels, whereas in MMC the number of device count increment will be linear in nature. So if I want to increase the number of levels, I will have to increase the modules or the devices in linear manner. So when I have higher number of levels, the number of device count in MMC will be less compared to the multi-level converters, and it has high power capability, and it is perfectly modular, so it is scalable and it is having higher reliability. Then we have seen the working of that. In that we have seen that some modules which are present in the upper and lower arms, they will be selectively inserted to generate a particular voltage level at the output AC terminal. So 50% of the sum modules in the entire leg will always be in the bypass mode. That's what we have seen. Why this 50% will be in the bypass mode? To satisfy the cable in the outer loop, and the distribution between the number of sum modules inserted in the upper and lower arm will be depending on the instantaneous AC voltage which is required at the output terminals. So now as the capacitor will be inserted in the current path, when the current is flowing through it, depending on the direction of current, the sum module capacitor will be charging and discharging. So that's why we require this algorithm which is called as our sum module selection algorithm. So in this algorithm, if you see what is done, we sense all the sum module capacitor voltages, then sort them at every sampling time, and we sense the arm current. Based on whether my current is positive or negative, we take the decision on selecting the number of sum modules. Okay, so where small n is the number of sum modules required in the upper or lower arm. Okay, so suppose for example, consider we are dealing with the upper arm now. So n will be the insertion index of the upper arm. So now if I, as per our example where we had 4 number of sum modules, so the small n value can be varying between 0 to 4, where 0 stands for all the sum module in the bypass state, where 4 stands for all the sum modules in the inserted condition. So for these two conditions at the boundary stages, we will not have any redundancy, or there will be no meaning of selection of sum module, because all of them are either bypass or inserted. So we will be selecting the sum modules when we have the insertion index number between 1 to 3. So suppose now I want to select one sum module and the current at the time is positive. So it will go into this and I will select the sum module which will be having the least voltage. Why? As the current is positive, whichever sum module capacitor will be inserted in the path, or whichever sum module will be inserted, its capacitor will behave as a load or it will get charged. So I will insert the sum module which is having least voltage. If the vice versa condition is true, then I will insert the small n number of sum modules which will be having higher voltage, such that they will get discharged. When I do this operation over a cycle of fundamental AC, I will observe that the net amount of charge being removed or dumped inside the capacitors will be equal. That is, they will be equally charging and discharging over a cycle after implementing this sorting algorithm or sum module selection algorithm. So now what is required? So who will pre-charge the capacitors? Once the pre-charging is done, this sorting algorithm will maintain that at that particular voltage. That for pre-charging we have various types of mechanism: self pre-charging, dedicated pre-charging circuits where we will be having DC source which will be charging them. So we will not go into those details of the circuits. So if you are interested, you can refer to some standard papers. So now we have seen the application of our MMC in the electric vehicle. So here we have connected DABs. In place of DAB, we can have any type of isolated DC-DC converter. The isolation will be required because these some modules are floating in nature. Now the other solution is our IPT, or inductive power transfer, or wireless power transfer. Okay, so that we will be seeing today. So in place of DAB or any isolated DC-DC converter which can be placed over here, I have other option, that is going for wireless charging. Okay, so as the name suggests, wireless, so there will be no conducting wire between the charger and the electric vehicle. So how that is done, we will see that shortly. So for those type of applications, here MMC can be used, where we want multiple charging ports, or where we want high power density converter or an converter which can handle high power. So, the other utilization of our MMC was in the DC to DC conversion stage, where we have an high voltage on one side and low voltage on the other side. So, we can use the MMC which will be having an high power handling capability. So, where this can be used in the SSTs or to power the charging stations. Okay, so our SSTs can be used to design DC fast chargers or an public charging station. What is in public charging station? It is a replacement of our conventional petrol pumps, where we just driving with the vehicle and fill our tank. Similarly, in public charging stations, we will drive with an electric vehicle which will be having less battery charge, or SOC will be nearly zero. We will charge it again and we will go with the battery full charge in condition. Okay, so we will be recharging the battery in the public charging stations. So, there, to minimize the waiting time or the charging time required to charge the vehicle, we want high power chargers, as well as we want plenty number of chargers, not a single charging point, but multiple charging points, so that waiting period and the time required to charge our electric vehicle from 0 to full load, full charge state will be reduced. So, there is another example where a multi-level converter is used in developing multi-port charger. So, in this way, I can use multi-level or our modular multi-level converters for developing various stages of my charger. So, I can use the same converter as a DC to DC converter, which we have seen in the last slide. Here we are using that same converter as AC to DC conversion. So, in both the places, as per my requirement, I can use this multi-level or modular multi-level converter to design AC to DC or DC to DC converter stage. Now, we were starting our discussion with the SSTs. So, what is the advantage of our conventional transformer? So, they are the low frequency transformers, that is 50 or 60 hertz, or the power frequency transformers. So, they are highly robust and reliable. Why? Because they are known to us since a long time. So, we know the technical know-how of them. Their efficiency is as high as 99.5 for power transformers. They are relatively inexpensive compared to the solid state transformers, which are new in the field. No capability of voltage and frequency regulation. We have understood that. What is the meaning of that? If the input frequency is changing, the output frequency of the transformer will also change. It will not be able to regulate by itself. Similarly, with the voltage, if the input side voltage is changing, so the same change or the proportional change will be reflected at the output terminals. No DC ports. I cannot connect my electric vehicle or an renewable energy source, because there is no DC ports available with me. So, it is having larger volume and weight, because it is designed for power frequency or low frequency operation. As the frequency of operation of the transformer increases, its size decreases. Okay. Now, the advantages of SST, the new technology which we are developing or using recently. So, here in this high power density, this compared to the previous conventional transformer, the SST will be having high power density. What is the meaning of that? For a given power rating, the volume of SST will be less compared to the conventional transformer. Instantaneous voltage regulation. So, we have understood that if the input voltage changes, the output voltage of the conventional transformer will automatically change, whereas in this case I can regulate them by using the controller present with the SST. Power factor correction. In conventional transformer, there is no scope of reactive power support or power factor correction in that. So, whereas in SSTs we can go for power factor correction by injecting or removing reactive power, as well as we can make the reactive power 0 or the current drawn from the source perfectly unity as per the reference set to the controller. Power quality monitoring and control. So, in that, as we are trying to maintain the power factor on the input side, so power quality will be better. So, what is the power quality? When I have sinusoidal voltage, harmonic free voltage at the supply, I say the power quality is better. So, those things to improve the power quality can be done by your SST. Outage compensation. If there is some, suppose primary side or secondary side has been disconnected due to some fault, there in that time, what is the operation of the conventional transformer? We do not have any scope of generating the reactive power, supporting the grid by reactive power whenever there is a fault. our grid always falls short of reactive power. So we want an converter or some system subsystem of our grid to support the grid by supplying reactive power. That can be done by our SST. That is what is the meaning of outage compensation. Now availability, when we go into the architecture, we will see that it will have various stages of conversion, and we will have two buses. One will be at an higher voltage, maybe in the medium voltage range or high voltage range, based on the application where we are designing the SST, and other one will be the low voltage DC link. So this low voltage and high voltage DC links can be used to interface your renewable energy sources like your solar and wind, and we can have storage, we can have electric vehicle also at the DC buses. So distributed energy sources, the renewable energies, that is our solar and wind. So these are the two popular sources used in our Indian grid. So solar, it by default generates an DC signal, so that I can directly connect to the DC port of the SST. Wind, it generates variable frequency AC. I will just rectify it, turn it into fixed frequency component, that is our DC or zero frequency component. I will directly connect it to the MBDC or HVDC or LVDC bus, based on the power rating of the wind farm. Okay. So if this facility was not available with me, I would have required one more additional stage of conversion, that is from the fixed DC to an fixed frequency AC. So that stage will be eliminated as SST has DC ports with it. Controllability, so it has higher controllability, as we have seen various factors which it can do, that is power factor correction, power quality maintenance, outage compensation, renewable energy integration. Those things are the additional features available with our SST. So it has better control facility. Easy interface with our communication and smart grid network. So in near future we will be having smart grid network. With that, this SST can be easily interfaced. Why? Because it will have an DSP or a microcontroller inside that to control the system, that can have communication with our network. Bidirectional active and reactive power flow. So SSTs, they will be meant with our fully controlled devices, so they can perfectly control the active and reactive power independently and in the bidirectional mode, that is input to output or from output to the input stage. That also we have understood what is the requirement of bidirectional in our electric vehicle, B to G, G to B or B to X. Those type of things can be done when we have an SST based charging station. Potential separation by using an medium frequency or an high frequency transformer. We have discussed that the size of the transformer will be proportional to the operating frequency. In SSTs, we will see that we will not operate that at the low frequency like our conventional transformer. We will either operate it at an high frequency or medium frequency based on the power rating. Fault isolation, if there is fault on the primary side, I can isolate it from the secondary side and vice versa. The fault current from one side will not be allowed to flow to the other side when I have SST, which was not possible with my conventional transformer. So in this case, whenever there is a fault detection, I will just set some contingent signals in the DSP, or I will send some contingent signal to the controller, and it will automatically bypass or eliminate or disconnect the faulty section from the healthy part of the circuit. So once there is a fault on the primary side, it will ensure that no current flows from the secondary side into the faulty side of the system. So that facility is available with our SST. Now what is our SST? So here we can see the SST has various stages of conversion. First is we have medium voltage or high voltage system based on the rating for which this and the area for which this SST is designed. The first stage will be our AC to DC, where we will convert this 50 hertz or 60 hertz. This will be at 50 or 60 hertz AC, that I will be converting into DC. Then from DC, I will be converting it to high frequency or medium frequency. If my power rating is very high, instead of going into high frequency, I will go for medium frequency, because if I have higher power rating, so the operation frequency, if I operate it at very high frequency, the switching losses will be very high in the conversion stages. So when the power rating is very high, we go for medium frequency instead of high frequency. If we have an MDC or electric vehicle type of applications, at that, for those applications or at that power level, I can operate the transformer at high frequency. So now we have got DC, so we will have an DC to AC conversion stage that will convert the DC into an high frequency or medium frequency AC, and we will have an transformer in between. Okay. Then after that, the transformer converts the voltage based on the relation between the input and output voltage. We will have an appropriate turns ratio 1:1 based on the ratio between your input and output, or the MVDC and LVDC, or HVDC and LVDC bus voltages. Then this high frequency AC will be converted into DC. Then from the DC again we will convert it into low frequency AC, that will be again our 50 Hz system for our Indian grid condition. So, here if you see, just to eliminate our conventional transformer, we have added 4 different stages of conversion. So, how we say that the SST will be beneficial, because the complexity of the system has become very high. So, here in this case if you see, the main advantage is again we have an transformer over here. Okay. So, from shifting from conventional to SST, we are not eliminating the transformer, just we are shifting the operating frequency of the transformer to an higher frequency, so that its size will be much less. So, how it is quite surprising that it has this many stages of conversion, and I still say that it will be having an higher power density. So, how that is possible? So, if you see, compared to transformers which is operating at conventional frequency and the other one which is operating at high frequency, I will observe that the size of the transformer will be very less of the high frequency transformer for the given power rating, as well as it can eliminate the force oil cooling. In the conventional transformer or conventional power transformers, we generally have forced oil cooling, where the transformer core section and the windings will be immersed inside the transformer oil, and they will be uh, dissipating, they will be observing the heat which is generated because of the loss in the transformer, and they will go to the outward fins, where there will be an forced air which will be injected on the fins, and they will radiate the heat or the loss which were created inside the transformer core section to the outside atmosphere. So, those cooling arrangements can be eliminated because the size will be very less, so it can be air cooled. So, when we compare a transformer with the cooling arrangement, with the tank, oil tank and those things, we can see that the volume of this overall conversion, although it has many stages of conversion, the overall footprint or the power density will be higher when we go for SSTs. So, in this case, if you see what will be the application in our electric vehicles. So, here is an example where we have shown two different stages where our electric vehicles can be connected. First is, if I want to go for low voltage charging, I have an electric vehicle which can be charged with a slow charger, then I can select the LVDC bus and I can connect the charger. Suppose the source can be from the conventional AC grid, we can have the preceding stages. Similarly, when I select MVDC bus for connecting some fast charger, suppose I am developing a charging station which will be connecting multiple charging ports, or which will be having DC fast charging facilities, there I will be going for medium voltage systems where it can be 1500 or more than that. So, for those type of applications, I will be selecting the DC bus. I can have a low frequency conventional grid fed from the low voltage side. Then the DC to AC conversion, we will be having an AC to DC conversion over here. Then the DC to AC conversion, then high frequency, then our medium voltage DC bus will be the end of our conversion stage. So, here if you see what advantage we have got now, if we have this type of system. First advantage is I can connect the renewable energy over here. So, I can have a charging station or a charger which will be assisted from renewable energy. Yes, that can be done. I can just connect renewable energy sources over here, or if I have high voltage renewable energy generation for commercial application like our public charging station or DC fast chargers, there also I can have high power renewable energy integration, or I can increase the number of panels or number of wind farms, so that higher power can be generated, and this can be made self sufficient. That is, it will be generating the renewable energy, it will be feeding the chargers, and it will not depend on the grid for supplying the active power. Okay. So simultaneously we can have storage also at any bus as per our requirement. Maybe at the low voltage side bus we can have the battery or BESS system. Here also at the MBVC bus also we can have the battery. Okay. So in this way I can make the charging station green charging station or sustainable energy based charging stations by using my SST. So if we compare this solution where we have this component, that is battery, renewable energy, plus some conventional loadings on the buses, low frequency AC or at the DC stages, then when we go for SST, we will find that the number of conversion stages will be reducing because of this wide area of application or sources and loads, or there are many source and loads at different profiles. So I am integrating them. So when I count all of the components or the number of conversion stages, if they were meant to be connected to the conventional grid separately, and in this solution where everything is integrated, so I will see that the SST will be providing an better solution. Okay. So now let us see what will be the architectures of our SSTs. Based on the connections, there are 4 different architectures of SST. This is the first one which is shown over here, that is AC to AC conversion. So this is one architecture where we will be having an complete box which will be sensing or taking AC power at the low frequency, and it will be delivering the power at the low frequency without any conversion. The second option is availability of, or the DC ports can be taken out of the system. We can have only the high voltage DC bus and the LVDC bus along with our AC terminals can be considered. We will not have any facility of external connection. So that will be second architecture. The same way we can only have the LVDC bus and the two side of our AC buses. That will be the architecture number 3. The fourth architecture is where we have two DC buses and two AC buses. Okay. So based on our output ports available, we classify the architecture of SST. So in this way we can have 4 different architectures, where in the first we will only have 2 AC terminals, in the second architecture we will have 2 AC terminals plus 1 DC, in the third we can have the low voltage or high voltage DC. So that in that way we will have second and third architecture. In the fourth architecture we will have 2 AC and 2 DC buses. As per my application requirement, or how many renewable energy, how many buses loads are there, based on those things I will decide which architecture has to be selected, and I can eliminate the conversion. That is, it does not require, suppose I do not have any low voltage AC load to be connected, then I can eliminate the stage of conversion. I can end the SST at this point. Okay. So I can have an LVDC which will be connected to DC load or your electric vehicle charging loads and those things. So this SST is nothing but the use of the conversion stages which we have already discussed, that is AC to DC and DC to AC we have already discussed. So those can be used in our SSTs as per the application requirement. Okay. So we can use any MLI or our MMC, the single stage of conversion. Okay. So if I go for, suppose for example I am considering MMC to develop an SST. So here we will have one MMC which will be converting the low frequency AC to DC. Then we will have another MMC which will convert the DC to high frequency AC. Then another MMC over here which will convert the high frequency AC to DC. Again another MMC which will convert the DC to a conventional frequency AC. Okay. Similarly, I can use any MLI as per my requirement. Now, the next topic is our wireless power transfer. Okay. So what is a wireless power transmission? So in this transmission, there will be no wired connection between the source and the load. Okay. So that's what is the meaning of wireless. So we will not have any connecting wires between the source and the load. So wireless power transfer is of two types: far field transfer and near field transfer. As the name suggests, so far field transfer are not good candidates for electric vehicle application because the source and load will be very much far away from each other. Based on the distance, we classify this as far field or near field. For our electric vehicle application, near field transmission is better, where the receiver and the transmitter, that is our electric vehicle, and the source for that charging will be located at a distance limited to few tens of centimeters. Then what are the advantages of this wireless power transfer? Convenience, no cable handling. So how we are charging our conventional charger based system? So in that cable based system, we have to bring the electric vehicle near the charging station or the charger. We have to connect the charging plug inside the vehicle. Then our communication signal will be exchanged based on the BMS command. Your charging will start and the battery will be recharged. Whereas in this case, there is no requirement of your external wire connection, or the cables, they are no longer required to be connected. I just need to bring the vehicle over the charger and the power will be automatically transferred. Galvanic isolation, it is safer because in the first case we have conducting wires, there can be electrical hazards, whereas in this case we have isolation, there is no connecting wires, so it is safer. The other way is reliability, no wear and tear. So we do not have any charger plug or any wires to be connected between the two systems. They are perfectly independent from each other. So the reliability will be better over here. Weather immunity, so as there is no connections and the charger and the electric vehicle will be not be coming in the physical contact, so they will not be dependent on the weather conditions. Then automatic charging. So here in this case, the moment vehicle comes in the proximity of my charger or the transmitter, the power will be transmitted and our electric vehicle will be charged. Few maintenance requirement. So here as the wear and tear is less, our maintenance will be less. Dynamic charging possible. So in our conventional charging, what is the main demerit? Suppose I am having an ambulance which is based on electric vehicle. Okay, then there is some emergency, I cannot stop the vehicle in between to charge it, or there can be various repercussions or various demerits of having downtime for an emergency service vehicle. So during that stage, what is the option available with us? I can have dynamic charging. So what is the meaning of this dynamic charging? So in the next slide, we will go into the types of wireless power transfers. So before the dynamic charging is charging in motion, or the vehicle will be running itself and its battery will be charging. So we will have an road or any truck where the chargers or the transmitters will be connected inside the truck, and while the vehicle is moving over the track, it will be charged. Okay, so there will be zero downtime when we go for wireless power transfer. Okay, so what is downtime? The duration for which my electric vehicle is not in service. Okay, so maybe if I go for fast DC chargers, there it will be out of service for 10 to 20 15 to 20 minutes, whereas in this dynamic charging cases, so the downtime of the vehicle or the charging time of the vehicle will be zero, because it can be charged while in the motion. Independent of charger connection types, connector types. So we have gone through the types of connectors in the last few lectures, where we have seen that we have many types of standards and many type of connectors. So in the wireless charging, there is no connection between the electric vehicle and the transmitter coil or the source of the energy. So it is independent of the charger type. Okay, so or else if we do not have wireless power transfer, I have to select or particular charging port or a charging station which will be compatible with the connector which is available with my electric vehicle. Okay, so those limitations are eliminated when we go for wireless power transfer. So every advantage has some limitations. Now what are the challenges of our wireless power transfer? First is misalignment of the charger. Okay, so what is this misalignment? Suppose I have the transmitter coil, and my suppose the vehicle is not placed exactly above it, but it has moved ahead. Okay, so then I see this condition as misalignment, that is the source and the electric vehicle are not perfectly aligned, or their position is not as per the requirement. Okay. So during the stage, the efficiency of the power transfer will be decreasing. We will see those in the next few slides. Cost effectiveness. So here I will see that it will also have various stages of conversion, so it will be bit costlier. So the main requirement is from the cost side. Maintenance requirement, now we will have, suppose we have dynamic charging or we have wireless charging, so various stages of conversion are there, so their maintenance will be required. It will be having various stages of power conversions, which we will be seeing what will be the stages of power conversion. So each stage will have some power trans component, so their size optimization, efficiency improvement, those things require huge amount of research and investment. For an object detection, suppose I have and transmitter coil, instead of electric vehicle some other component has come into picture, I have to detect that and I should not send any power, or else there can be some hazard. Okay, so that is one more challenge. Communication, as we are just transferring the power wirelessly, as I said in the during the conventional transformer, when I connect the charger, there will be a communication between the vehicle and the BMS of the vehicle with the charger. Then after the communication is established, then my charging power starts. Okay, whereas in this case the communication will be a challenge because there is no wire between the source and the load, so communication becomes a bit challenging in this case. Now let us see what are the types of wireless charging. Okay, so specifically for our electric vehicle applications, we have three different types of charging modes. First is your inductive power transfer based wireless charging, then capacitive power transfer based wireless charging, hybrid power transfer, where we will have both of them, that is inductive and capacitive. Each one of them can be further classified into two different types based on the status of the vehicle when it is being charged. First is static, as the name suggests, the vehicle and the charger will be at the rest, or when the charging is going on the vehicle will not move, then I say that it is an static wireless power transfer. Quasi-static, so it the vehicle will be at halt when it is charging, but the charger will be located at specific locations. We will see the details in the next slide. Dynamic charging, so we have already discussed this, while the vehicle is in the motion it will be charging. So now inductive power transfer, so the power transports in the way of magnetic field. So we will have two coils, they will be generating the magnetic field and the power will be transferred from the source to the load side. So IPT is quite popular compared to the other two methods for our electric vehicle application, because the operation frequency over here will be 85 kilohertz, or the AC signal which will be generated between the gap will be at 85 kilohertz. So we will see that in the next slide. So because of that it will be having a higher power density compared to the other two methods. So IPT is more popular. So when I say wireless power transfer, it should come into the mind that will be your inductive power transfer. Okay, the other technology is your capacitive power transfer, where we will be transferring the power by using the capacitance principle, that is it will be establishing an electric field between the electric vehicle and the charger. By that way the power will be transferred. The third option is our hybrid power transfer, where they will be using both electric and magnetic field to transfer the power. Now static charging, the other way of classifying this static charger. So here the receiver is placed aligned with the transmitter, then here our power transfer will be taking place, that is the vehicle will not be moving when we have static charger. Dynamic charger, it will be charging when it is in the motion. We have already discussed this, the vehicle will be moving and simultaneously it will be charging. So for that we will be having dedicated charging routes, where we will have the transmitter coils, and the vehicle when it is still in the motion it will see the transmitting coil in its proximity and the charging will be starting. Then quasi static, so it is a type of static charging, that is where the vehicle will be designed to stop, that is your bus stops or then traffic signal or laybys or the rest areas of your highway, there I will be placing the charger. Okay, so while suppose for example let us consider a bus stop, so we know that the bus which is electric vehicle will come at that bus stop, it will be halted for around 1 to 2 minutes. So when the passengers will be getting on board or they will be deboarding, so during that time my power transfer cannot take place. So that what will be the advantage of having this quasi-static charging? Again, I am reducing the downtime of the vehicle. So this quasi-static charging, it is a hybrid combination of dynamic plus static. That's what we can say, that the vehicle comes to the charging station, stops there, but it is not the downtime of the vehicle, it is the required stoppage, like traffic signal. If the traffic signal is red, so we will not be able to cross the traffic signal, so we will be waiting. So during that time my vehicle will be charging. Okay, so this is the way of classifying your wireless power transfer. So in this lecture we have seen our advantage of SSTs and the tentative application of SST in our electric vehicle. Then we have started our discussion on wireless power transfer. We have seen the different types of wireless charging and different technologies for wireless power transfer. We will continue from this point in the next class. Thank you.